we present our work entitled Transformer-Based Unified Recognition of to Hands, Manipulating Objects. Recently, there have been efforts to understand hand-object interaction. However, most methods focus on the separate problem either for the pose estimation or for the interaction recognition. Furthermore, pose estimation methods are developed based on the already cropped, bounding boxes of hand and object. To tackle these challenges, we propose the transformer-based unified framework to estimate poses of to hands, object poses, object types and interaction classes between hands and object. Here is an example result of our proposed method. This video showcases the estimated 3D skeleton and mesh representations of hands and objects, along with the corresponding contact map and interaction class. In previous works, Tick and al. proposed an unified framework that estimates the 3D hand pose, the object 6D pose, and their action classes. They developed the pose estimator extending the architecture of YOLO towards 3D space and recognize actions using estimated hand and object poses. The LSTM-based architecture is further used to map the information towards the interaction classes. Quan et al. Further extended the framework towards involving to hands, rather than one hand. The proposed method involves the GCN to model the hand-object interaction, considering the geometric relation between hand and object. However, their results exhibited suboptimal performance. Our contribution is as follows. First, we proposed the transformer-based unified framework for estimating poses of to hands, object poses, object types and hand-object interaction classes at a single inference step. Second, we introduce a novel interaction recognition method which utilizes a contact map. To the best of our knowledge, this is the first work to exploit the contact map as a cue for interaction recognition. Last, we achieve the state-of-the-art performance in pose estimation and interaction recognition tasks using H2O and FPHA datasets. This is schematic diagram of our framework. We will explain the framework step by step. Firstly, we predict the pose of the hand and object, as well as the object type, for each frame of the video using a hand-object pose estimator. We design the hand-object pose estimator using a transformer-based approach. The feature extractor extracts the multi-scale image features from image X. Afterwards, positional embedding is added to the image features, and this combined representation serves as the input to the encoder. The input features are updated in encoder. Object queries in the decoder extract features vectors from the encoder's output, feature maps, and are updated through attention operations. Finally, the updated object queries are fed into the prediction head to predict sets of hand poses, object poses and probability of object types. To train pose estimator, we search for the permutation with the lowest cost to find a bipartite matching between prediction and ground truth. The cost function is as follows. The loss function is same to cost function and calculated for all pairs in the best permutation, sigma hat. It consists of classification loss and pose loss. Variations in poses of hands and objects are important cues for recognizing interactions between hands and objects. However, we observed that recognizing interactions solely based on the poses of hands and objects is non-trivial in many cases. For example, as shown in figure, the two videos corresponding to the interaction classes open chips and take up chips show that hands move away from the object over time. The relative movement of hands and objects are similar in two videos. It is non-trivial to discriminate their interactions based solely on the pose information. It leads to confusion between action classes with similar poses. Therefore, we exploit the contact map between hand and object meshes. We visualized the contact map that is able to explicitly represent the part where two hands and an object are contacted. We think this is a more effective clue to recognize the interaction between hands and objects, even when their poses are similar. In figure, the first row is a frame from the Open Chips video, and the second row is a frame from the Takeout Chips video in H2O dataset. For interaction recognition, we select the queries corresponding to the left hand, right hand, and object based on their class probability among all the object queries. To generate the contact map, we need to hand mesh and object mesh. We take the inverse kinematic approach. As a result, the hand mesh vertices can be obtained. The object mesh is given. Object 6D pose is recovered by applying the rigid alignment between the predicted object 3D pose and the ground truth object 3D pose. We transform hand vertices and object vertices to same space and generate the contact map based on distance between each vertex and its nearest neighbor. The contact map is computed using the following equation, where ρ is the sigmoid function, d is the distance function for calculating the distance between vertex v, I, and its nearest neighbor vj. Finally, we input the hand vertices, object vertices, contact map, and object type probability for each frame, along with the action token to the encoder layer, to predict the interaction class. We use cross-entropy loss as the loss function for training. These tables show state-of-the-art comparisons on H2O and FPHA datasets. Our method outperformed all previous works and achieved the state-of-the-art accuracy for hand object pose estimation and interaction recognition. We validated our design choices regarding reference point refinement, the number of sampling points, and the using the contact maps. This figure shows the examples of hand object poses and interacting classes on H2O dataset. First row is input frame, second row is contact map in interaction space, third row is contact map in canonical poses, and last row is estimated hand object poses and interacting classes. This figure shows the examples of hand object poses and interacting classes on FPHA dataset. Thank you for watching.